What specific problem does PokéChamp aim to address in the context of Pokémon battles, and how does this differ from traditional reinforcement learning approaches?
PokéChamp aims to address the limitations of planning capabilities in text-based language agents within the context of Pokémon battles, which are characterized by a vast state space and partial observability. Unlike traditional reinforcement learning approaches that require extensive task-specific training and exhaustive exploration of the game environment, PokéChamp leverages a large language model, LLM, to enhance a Minimax tree search algorithm without the need for additional training on Pokémon-specific data. This integration allows PokéChamp to propose strategic actions, model opponents based on historical data, and evaluate game trajectories effectively, thereby reducing the computational burden associated with exhaustive search methods. The agent's design focuses on utilizing pre-existing knowledge from the LLM to navigate the complexities of Pokémon battles, contrasting with traditional methods that rely heavily on iterative learning and reward optimization. Ultimately, PokéChamp achieves expert-level performance by combining LLM capabilities with game-theoretic planning, showcasing a novel approach to tackling the intricacies of competitive Pokémon gameplay.
How does the proposed method, PokéChamp, work? Please illustrate it step by step, detailing the roles of the Minimax algorithm and the integration of large language models in each phase of the process.
PokéChamp operates by integrating large language models, LLMs, into a Minimax tree search framework to enhance decision-making in Pokémon battles. The process begins with player action sampling, where the LLM is prompted with the current game state, team strategy, and battle history to generate a set of viable actions for the player. Next, opponent modeling is performed, where the LLM predicts likely actions of the opponent based on historical data and the current observable state, addressing the challenge of partial observability. The third phase involves value function estimation, where the LLM evaluates the potential outcomes of actions at a limited depth in the Minimax tree, replacing traditional terminal rewards with LLM-generated scores that consider various game dynamics. The Minimax algorithm then uses these components to navigate the search tree, selecting actions that maximize the player's expected reward while minimizing the opponent's potential gains. This integration allows PokéChamp to effectively manage the complexities of Pokémon battles, achieving expert-level performance without requiring task-specific training.
Can you explain an example scenario where PokéChamp is employed in a Pokémon battle? Walk through the steps of action selection, opponent modeling, and value function estimation using this example.
In a Pokémon battle scenario, PokéChamp begins by observing its current info set, which includes its own Pokémon's health, moves, and the visible opponent's Pokémon. For action selection, it utilizes the player action sampling module, where it prompts the LLM with the current team strategy, observable state, and battle history to generate a set of viable actions. For instance, if PokéChamp's active Pokémon is a water type, it might consider using a strong water type move, or switching to a Pokémon with a type advantage. Next, in the opponent modeling step, PokéChamp predicts the likely actions of the opponent based on historical data and the current game state. It estimates the opponent's hidden stats and possible moves, allowing it to infer the most probable actions the opponent might take, such as attacking or switching Pokémon. Finally, for value function estimation, PokéChamp evaluates the potential outcomes of its actions by generating a score for each possible move based on factors like the effectiveness of the current moves, the number of remaining Pokémon, and the opponent's strengths. This score helps determine the optimal action to take, ensuring that PokéChamp maximizes its chances of winning while navigating the complexities of the battle. By integrating these three components, PokéChamp effectively makes informed decisions in the dynamic and partially observable environment of Pokémon battles.
What are the theoretical or practical benefits of using PokéChamp compared to existing heuristic bots and LLM-based agents in Pokémon battles?
PokéChamp offers significant theoretical and practical advantages over existing heuristic bots and LLM-based agents in Pokémon battles. Theoretically, It integrates large language models, LLMs, into a Minimax tree search framework, enhancing decision-making through improved player action sampling, opponent modeling, and value function estimation, which allows it to navigate the complex, partially observable state space more effectively than traditional methods. Practically, PokéChamp achieves superior performance metrics, such as an 84% win rate against the strongest heuristic bot and a 76% win rate against human players, demonstrating its capability to compete at an expert level without requiring task-specific training. Additionally, it leverages a comprehensive dataset of over 3 million Pokémon battles, enabling it to model opponent strategies and adapt to various competitive scenarios, which is a marked improvement over existing agents that often rely on fixed heuristics or limited training data. This combination of advanced modeling techniques and extensive empirical data positions PokéChamp as a state-of-the-art solution in the competitive Pokémon landscape.
How was PokéChamp validated? What experimental design, datasets, benchmarks, and metrics were used to demonstrate its performance and effectiveness during evaluation?
PokéChamp was validated through a comprehensive evaluation strategy that included both offline dataset analysis and online gameplay on the Pokémon Showdown platform. The experimental design involved comparing PokéChamp against established Pokémon bots, including heuristic-based and state-of-the-art LLM-based agents like Pokémon, across various competitive scenarios, specifically in Generation 8 random battles and Generation 9 overused meta formats. The evaluation utilized a dataset of over 3 million Pokémon battles, which provided rich information for opponent modeling and strategy development, and included benchmarks such as version 1 battle scenarios and puzzles designed to test the agent's understanding of game mechanics. Performance metrics included win rates, with PokéChamp achieving a 76% win rate against human players and an ELO rating of 1300 to 1500, placing it within the top 30% to 10% of competitive players. Additionally, the evaluation included action prediction accuracy, demonstrating that PokéChamp significantly outperformed random predictions, thus validating its effectiveness in navigating complex, partially observable game environments.
What specific limitations or drawbacks did the authors acknowledge in the performance of PokéChamp, particularly in the context of handling certain strategies during gameplay? And what implications do these limitations have for its real-world application?
The authors acknowledged that PokéChamp struggled against specific strategies, particularly stall tactics and excessive switching, which were challenging due to the limited look-ahead depth imposed by time constraints. This limitation hindered the agent's ability to accurately model and counter such strategies effectively during gameplay. Additionally, they noted that human players who were aware they were facing PokéChamp could exploit these weaknesses by tailoring their strategies to take advantage of its excessive switching behavior. These drawbacks imply that while PokéChamp demonstrates expert-level performance overall, its effectiveness in real-world applications may be compromised against skilled opponents who can adapt their tactics to exploit its limitations. Consequently, this highlights the need for further refinement in the agent's strategic adaptability to enhance its robustness in competitive environments.